Hi children, in the previous class you studied about electrostatics part 1. In that one, till Coulomb's law statement is seen. Now let us see some more in the electrostatics chapter part 2. Say electric field. In the chapter gravitation you might have studied gravitational field, like that. Electric field is a region, three-dimensional region surrounding a charge within which another charge can experience a force. Electric field is a region, three-dimensional region where a charged body can experience a force on any other charge. And this field will have different intensity at different places. Just consider a bulb, glowing bulb. Nearer to the bulb, its intensity of the light is more, but as we move away from the bulb, the intensity of light decreases. Like that, nearer to the charge, the intensity is more, and far away from the charge, the intensity goes on decreasing. So let us define the electric field intensity, which is a vector quantity which is represented by capital letter E. And electric field intensity, say this picture, this is a positive charge, and I need to find the electric field intensity at P. So for finding the electric field intensity at P, we keep a test charge. Test charge means plus 1 Coulomb charge. Keep a test charge at P. So this charge will experience a force on the test charge, and that force is a measure of electric field intensity at that point. Force experienced by a unit positive charge, which is known as test charge, kept at that point. See this? We can see a positive charge is kept there, and a test charge is brought at different places nearer to it, and see the length of the arrow, and the length of the arrow represents the magnitude of the force experienced by the test charge by this. So here you can see a weak field means far away from the charge, and a strong field means nearer to it. And this capital Q is known as source charge. I will show it once more. You see this? Capital Q, which is producing the field, is called source charge, and the test charge is represented by Q0. So let us get the expression for electric field intensity, and from the definition, electric field intensity can be defined as force per unit positive charge, that is vector E equal to F by Q0. And since force is a vector quantity, charge is a scalar quantity, but when you divide a vector by a scalar, the answer is a vector. So electric field intensity is a vector quantity. And see the bottom one. Here you can see a positively charged source charge is kept here, and you can see the movement of test charge, which is away from the source charge because it is a positive charge. So direction of the electric field intensity is same as the direction of the force experienced by the test charge, and since it is the positive charge, the direction is away from the positive charge. So electric field intensity is a vector quantity with both magnitude and direction. One of the expression for electric field intensity is this, vector F by Q0. Now let us see another formula for electric field intensity. See this figure, a positive charge plus Q is kept at the origin. Imagine a three-dimensional figure. A positive charge Q is kept at the origin, and we need to find electric field intensity at P, which is in space. And this point P can be represented by the position vector R, and the point P will have all the three coordinates x, y and z. So, the force between the charge plus Q and Q0 is given by Coulomb's law as vector F equal to K into Q0 divided by R square R cap. And see the definition for electric field intensity, which is force per unit charge. So, divide this force divided by Q0, you will get expression for electric field intensity at another equation, which is KQ by R square R cap. Just see the factors on which electric field intensity depends. As seen here, electric field intensity is directly proportional to the charge, means source charge, and inversely proportional to the square of the distance. So, we can represent graphically like this. Graph between electric field intensity and R square, since it is inversely proportional, the graph is a parabola. So, two expressions for electric field intensity, one is F by Q0 or KQ by R square R cap. Now, we can get the pattern of electric lines of force. You see, electric field due to a point charge is spherical symmetry. What does it mean? If you are keeping a point charge in space, surrounding the charge in three-dimensional space, there is field. And if Q is greater than 0, means that if it is a positive charge, then the field is radially outward. That means along the radius and outward. And if Q is less than 0, means it is a negative charge. And see the direction? Direction of electric field is towards a negative charge and away from a positive charge. See this? Force experienced by a test charge is same as electric field intensity. So, what is the force experienced by a charge of Q? Simply unitary method, F is equal to Q into E. That is the force experienced by a charge kept in an electric field of intensity E. And let the charge Q be an electron. Then what is the force experienced by the electron? You know that charge of the electron represented by small letter E. Then force on an electron is E into capital letter E, small letter E into capital letter E, where small letter E is the charge of the electron. And see the movement of a charge under the action of the electric field. You see, left picture shows the movement of a positive charge by the force of QE, and see the direction. The positive charge is moving in the direction of the electric field. But if it were an electron, as seen here, direction of electric field intensity is from right to left, and the electron will move from left to right. So, positive charge will move in the direction of the field and negative charge will move in a direction opposite. Let us see the unit also for electric field intensity. E is equal to F by Q0, and unit of force in SI system is Newton and unit of charge is Coulomb. So, the SI unit of electric field intensity is Newton per Coulomb, and as I told you, since force is a vector, electric field intensity is a vector quantity. So, unit of SI unit of electric field intensity is Newton per Coulomb. Similarly, what may be CGS unit? Dyne divided by stat Coulomb. And see this figure, the point P is in the field of many charges, Q1, Q2, Q3 and so on. And since the point P is in the field of many charges, we can find the resultant electric field intensity at P. And try to remember principle of superposition of charges we utilize for calculating the force on a single charge by many other charges. Like that, electric field intensity at P due to many charges can be written as the vector sum of electric field intensity due to the individual. See this? P is the point which is at a distance of R1P from the charge Q1. Similarly, the charge Q2 is at a distance of R2P from the point P. So, E1 can be written as 1 by 4 pi epsilon 0 or simply K Q1 divided by R1P square R1P cap. And same way E2 can be written as, vector E2 can be written as K into Q2 divided by R2P square R2P cap. So generally if there are n number of charges are there, we can use a sigma notation like this. Already seen for the resultant force on a single charge by many charges. Okay. Now let us see electric lines of force. Earlier I told you about electric field, intensity at a point is the force experienced by a test charge. So if the test charge is free to move in a field, that test charge will follow some path. Just see this. Q greater than 0 means it is a positive charge, and see what happens to a test charge. Test charge is moving away from the positive charge, and if Q less than 0 means negative charge, and the charge is moving, test charge is moving towards the negative charge. And these paths followed by a test charge is named as electric lines of force. And electric lines of force, two more names are there, electric flux lines or electric field lines. Electric field lines or electric flux lines. So let us see this one. Electric lines of force, this is due to a positive charge, and when you keep a test charge surrounding a point positive charge, everywhere the test charge will be pushed away and it will be along the radius. So those lines are known as field lines or flux lines due to a positive charge. And what is happening to the negative? The charge is getting, test charge is getting attracted towards the negative charge when the test charge is kept anywhere. So this is the electric lines of force for a negative charge, and see this picture. What is the arrow shows? The test charge will move away from the positive charge and traces some lines, and those lines are known as electric lines of force. See this another diagram. This is the diagram from your textbook. I will show the previous once more. You see, here I have drawn continuous lines as electric lines of force, but just see this. Observe very carefully. You see, it is a collection of arrows, and this is the vector diagram for electric lines of force. Means, in other words, it gives the strength of the electric field also at different places. You see, nearer to the positive charge, the arrows are larger in length, shows that field is stronger. Then gradually the length of the arrow is decreasing, and this is the vector diagram for electric lines of force, and the arrow represents the strength of the electric field. And if it is vector diagram, you have to draw like this. But to draw simply the electric lines of force due to a positive charge, you can draw straight line like this. Now I will show you the pattern of electric lines of force in different cases. First, to see this. Electric lines of force between two oppositely charged plates. Oppositely charged plates, see, it is actually a three-dimensional figure. Positive plate is onto the left and negative plate, which is blue in color, onto the right. And see, the green arrows represents electric lines of force originating from the positive charge and reaching the negative charge. And one more thing you can see, we will study it later in detail. The field is uniform, represented by equidistant and parallel lines. That is from a positive charged plate to a negatively charged plate, that is between two oppositely charged plates. Now see this one, electric lines of force produced by a thin positively charged plate. Red is a positively charged plate, again it's a three-dimensional figure, and see the arrow. On to the right, the arrows are away from the positive, and to the right, and behind the plate we can see the green lines which is directed towards the left. That is due to a thin positively charged plate. And see this one, electric lines of force produced by a thin positively charged rod like this. I can charge this rod, and from the rod, see, all around the rod electric lines of force are there, and see the direction away from the positively charged rod. And if it were a negatively charged rod, pattern will be same, but only the difference is an arrow. Arrow will be towards the rod. That is for a single thin positively charged rod. And see this one, positively charged, point positive charge and point positive charge. Two positively charged point charges are kept nearby. And see the pattern, electric lines of force due to similar charges of equal magnitude. And you can see the movement of positive test charge also you can see, because positive and positive will repel. So, see this point N. In this point N, the resultant electric field intensity will be 0. That means if you are keeping a test charge here, this left positive charge will repel it to the right, and the right positive charge will repel it to the left. So, since both the charges are equal in magnitude, both the force gets cancelled. So, this point N, where the electric field intensity 0 is known as null point or neutral point. And as seen in the picture, neutral point will be the midpoint of the line joining the two charges. See another one, electric lines of force due to a dipole. We will see the dipole in detail. See a dipole, and simply a dipole means two equal and opposite charges separated by a small distance. And see here, we can see the movement of a test charge from this positive charge to the negative. And see the exactly middle line, it is straight. So, positive and negative charge will attract, and that is due to a dipole. And here you can see another animated picture. See, that is due to a dipole, electric lines of force due to a dipole. And see, as this is the already shown you, two plates, positively charged plate and negatively charged plate, and this is the two-dimensional figure. And see the lines which are equidistant and parallel shows that field is uniform electric field. Just see properties of electric lines of force. They are imaginary lines. That means from the definition of electric lines of force, you have seen that they are the paths followed by a test charge when kept in an electric field. So, they are imaginary lines. A unit positive charge placed in the electric field follows the path, and those paths are called the electric lines of force. See the third property, electric lines of force will originate from a positive charge and terminate in a negative charge. Originating from the positive charge all around and terminating to a negative charge. Fourth property, just see another important property, the tangent to the electric field line at any point represents the direction of electric field at that point. Like that you can define electric lines of force in another way also. Electric lines of force are the lines which is used for finding the direction of electric field intensity at any point by drawing the tangent at that point. See this picture? P is the point on the line, and see the electric field intensity is represented by the vector. Next, fifth property, no two electric lines of force can intersect. What may be the reason for that? See this. It is actually related to this point. See, If two electric lines of force are meeting, compare with that, there will be two tangents at a single point which shows two different directions at a single point. Is it possible? No. So, no two electric lines of force can cross each other. Next, sixth property, let us see. They are closer or crowded where the electric field is stronger, and lines of force are spread apart where the field is weaker. Just see this, capital Q and small letter q. More lines of force are drawn here, capital Q, and only less line. Why it is so? Capital Q is greater than small q. So, larger is the charge, larger is the intensity, and crowded will be the electric lines of force. Say A, B and C. 3 point charges are shown with the electric lines of force. Simply by looking into the picture, can you say which charge is stronger or more in magnitude? A, B or C? Definitely it must be C, no? Because more number of lines are there and it is crowded. So, the number of electric lines of force originating depends upon the magnitude of the charge, which is another property. Next, see, electric lines of force are always perpendicular to the surface of positively or negatively charged body. That is why when you draw the electric lines of force due to an isolated point positive charge, you have to draw the lines perpendicular to the charge, that means along the radius. And just see this one, a plate, positively charged plate is there, and see the electric lines of force how it is drawn, perpendicular to the surface. And this is an irregular shaped body. Everywhere electric lines of force are originating perpendicular to the surface. When you draw the picture, it must be very clear. It must be drawn perpendicular. They contract lengthwise to represent attraction between two unlike charges. See? Attraction between two unlike charges, they contract lengthwise. But what happens if it is like charges? They exert lateral or sideways pressure to represent repulsion between two like charges. Next, see, the number of lines per unit cross sectional area, delta n by delta A, means that number of electric lines of force per unit cross sectional area is directly proportional to the intensity of electric field. Larger is the intensity of electric field, more will be the number of electric lines of force passing through unit cross sectional area. Next, let's 11th property. They do not pass through a conductor. Another interesting property, you see, in between a positively and negatively charged plate, a conductor, either a solid or a hollow, either a solid sphere or a hollow sphere is kept. And inside the conductor, electric field intensity will be 0. And the reason for that one you will study in the same chapter little later. It is as per another equation, and that fact is that electric field intensity inside a conductor is 0 is known as electrostatic shielding. Inside a conductor, electric field intensity 0. See this picture? In the electric lines of force, a rectangular shaped conducting ring is kept. Inside it, it is written there E equal to 0. That means electric lines of force will not pass through the conductor. And electrostatic shielding is the fact that inside a conductor, electric field intensity always 0. In relation with this, I will give you a simple example. During lightning, suppose you are in a car. During lightning, it is better to be inside the car than outside, standing out. Because the car is made up of metal, and since you are sitting inside the car, it seems to be a hollow conductor and no electric field will be inside it. It is due to electrostatic shielding. And see the last property, they can pass through insulator. Electric lines of force cannot pass through a conductor but can pass through insulator. These are the major properties of electric lines of force. 12 properties are there. See, I already mentioned about electric dipole. Electric dipole is a positive and negative charge of equal magnitude separated by a distance. And the electric lines of force already told. Positive charge and negative charge of. So, in simple words, how to define an electric dipole? A system of equal and opposite charges separated by a small distance is called an electric dipole. Equal and opposite charges separated by a very small distance. And this will be a single system, and this single system of charge will have a strength, and the strength of that single dipole is named as dipole moment, M-O-M-E-N-D, dipole moment represented by small letter p. When you write very clearly, small letter p, again it is a vector quantity. So, let minus q and plus q separated by a distance of 2a. That is a common way of representing the distance between two charges in a dipole, either 2a or 2l. So, what may be a distance from the center to any one of the charges is a. So, total distance, the common way of representing is 2a. So, electric dipole moment is a vector quantity which gives the strength of the dipole, and the strength can be written by equation like this. It is a product of any one of the charge and distance between the two. So, small letter p, vector small letter p is equal to q into 2a, but when you measure the length between plus q and minus q, the length is a scalar and charge is also a scalar. So, to represent dipole moment as a vector, we have to say that 2a is the displacement of the positive charge from the negative charge. So, 2a shows the direction of dipole moment. So, 2a must be from negative charge to positive charge. So, dipole moment direction is always from negative to positive, and the strength of the dipole is known as magnitude of the dipole moment, is the product of either charge and the distance between the two charges. So, equation for dipole moment is p, vector p equal to q into 2a, q into 2a. See, p, vector p is equal to q into 2a. So, how to get the unit from this? And SI unit of charge is coulomb and distance is meter. So, SI unit of dipole moment is coulomb meter. How to write that? Capital letter C with small gap and small letter m. But what will happen when you write small letter c, small letter m? It is only centimeter, that is wrong. So, SI unit of dipole moment is coulomb meter represented by capital C, small letter m. And see the dimensional formula for dipole moment. Dimension for charge is A into T and dimension for distance is L. So, dimensional formula for dipole moment is A T L. As you are aware that dimension, it must be represented by capital letter A, capital letters. So, capital letter A into T into L. That is a dimensional formula for dipole moment. Electric field intensity due to a dipole. And due to a single charge, already we saw the equation, vector E is equal to kq by r square. But let us find how to find the electric field intensity due to a dipole. For that, there are two major cases are there. The point P can be anywhere surrounding the dipole, but for calculation purpose we are finding the electric field intensity at 2 points on 2 lines. They are named as axial line and equatorial line. As seen here, axial line is the line passing through the two charges, axial line. And just see equatorial line, observe very carefully, just see. The line is passing through the center and perpendicular, or equatorial line is a perpendicular bisector of the dipole. First let us see electric field intensity at a point on the axial line. Axial line is a straight line passing through the two charges. As seen here, I have drawn negative charge here and positive charge here. You can draw anyway, either positive here or negative here. But with this picture I will tell you how to draw the figure, vectors. So this is the axial line. Let O be the center of the dipole. And what is the distance between the two charges named as 2a. So O2 minus q and O2 plus q will be a each. And this is the axial point, and let the charges are named as A and B. A is minus q and B is plus q. Now consider a point P which is at a distance of r from the center. Remember, P is in the field of both the charges, minus q and plus q. But will the intensity at P due to both the charges same? No, because q is plus q is nearer, but minus q is farther. So electric field intensity at P due to B will be to the right, because this is the positive charge plus q, and at the point P we are keeping a test charge which is again a positive, and positive will repel. So vector EB will be to the right, and see the magnitude, larger vector, but see the vector EA, and I have drawn small line, shows that electric field intensity at P due to the charge at A is less in magnitude because it is far away. So vector EB and vector EA are opposite to each other, and in vector addition, how to find the resultant of two vectors which are opposite? Say this, vector EP equal to vector EA plus vector EP, vector addition. Vector EP equal to vector EA plus vector EB, see the figure? And vector EA and vector EB are collinear and opposite. And as studied in vectors, if the two vectors are opposite in direction, the magnitude of the resultant is the difference between the magnitudes of the two. And here which is greater? EB greater than EA. So vector EB greater than vector EA. So what is the magnitude of EP? Simply EB minus EA. I didn't put the vector sign here, which shows that magnitude of resultant field at P is the difference between EB and EA. It must be EB minus EA because EB is greater. Now due to a single charge, I already gave the equation kq by r square, where r is the distance from the point to the charge, and see the figure, P is at a distance of r plus A from A. So what is the expression for EA? kq by r plus A the whole square along PB towards the charge. And what may be EB? B is at a distance of r minus A. So EB equal to kq by r minus A the whole square in the direction BP, that is to the right. So the resultant magnitude of the resultant field at P can be written as EB minus EA and EB is KQ by R minus A the whole square and EA is KQ by R plus A the whole square. And when you simplify this, denominator is the form as R minus A the whole square into R plus A the whole square, and on simplification you will get this answer. Modulus of vector EP, or simply the magnitude of electric field intensity at P, is K into 2 into Q into 2A into R. You know why I wrote Q into 2A within bracket? Yes, Q into 2A can be named as electric dipole moment, which is small letter p. So, equation for EP can be written like this: K into 2 into P into R divided by R square minus A square the whole square. So, or simply in a tune we can say like this: 2 kPr divided by R square minus A square the whole square is the magnitude of electric field intensity at P due to this dipole. And direction, what may be the direction? When you see the vector addition, if the two vectors are collinear and opposite, the direction will be towards the greater vector, and here EB is greater, so the direction will be in the direction of EB, that is in the direction BP, and negative charge is on to the left and positive charge is on to the right. So, direction of dipole moment already I told you, from negative to positive. Now compare the direction of EP and the dipole moment. What is the direction? They are in the same direction, see, same direction. And let us see one special case of that. If A is very much less than R, what does it mean? A is very much less than R means that if the dipole is a short dipole, we can neglect A from the equation, and when you simplify that, you are getting 2 Kp by R cube, and that is the equation to be substituted for or used for short dipoles and the distance is far away. EP, vector EP equal to 2 Kp by R cube, and just only the magnitude need to be written, EP equal to 2 Kp by R cube. And see the direction of dipole moment and the resultant intensity of the field at P, which is on the axial line, and just see, direction of dipole moment is from negative to positive. Direction of electric field intensity is also in the direction BP. So, how to conclude? The direction of electric field intensity at a point on the axial line is always in the direction of dipole moment. And derive this formula right from the beginning, understand the concept and derive it, and it is very simple, and be in a systematic way the derivation. And with this, let me wind up this class, and remaining part I will take in another class, that is electric field intensity at a point on the equatorial line, and it is possible to derive it yourself and try, or we can see my next class. Okay, thank you children.